Hello there, and welcome to the Sleepy Science Channel. Tonight, we'll explore some of the greatest mysteries of our universe and the remarkable story of how science uncovered their truths. For thousands of years, people tried to explain the world with stories and imagination. We saw lightning as a message from the gods, the sun as a burning chariot, and illness as a punishment from unseen forces. But slowly, patiently, we learned to look closer, to measure, to question, and to listen to what the universe was really saying. Every discovery began as confusion, a puzzle too strange to ignore. And each one brought us closer to understanding who we are, where we came from, and what this vast reality is made of. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, just breathe. Let your body relax and allow your mind to drift through these gentle science mysteries. Let's begin. For centuries, no one understood what kept the sun burning. For most of human history, the sun was a riddle that refused to make sense. A fire that burned without fuel, a star that never dimmed. Early astronomers imagined it was made of glowing coal or molten metal, but any material fire would have burned out in a few thousand years. In the 1800s, scientists calculated how long the sun could shine if powered by gravity alone, and the answer was devastating: only a few million years. Life on Earth clearly had existed much longer. Something far more powerful had to be at work. The truth emerged in the 20th century, when physicists discovered nuclear fusion, the process that fuses hydrogen into helium, releasing immense energy. In the sun's core, this transformation turns millions of tons of matter into light every second. The sun isn't burning in the way we once thought. It's shining through the quiet alchemy of physics itself, transforming matter into the energy that sustains all life on Earth. No one could explain how entire continents could move across the Earth. For generations, the world map seemed eternal. The shapes of continents appeared fixed, carved in their places since time began. And yet, there were clues. Identical fossils found on distant shores, matching mountain ranges separated by oceans, and coastlines that seemed to fit together like pieces of an ancient puzzle. In 1912, Alfred Wegener proposed the daring idea that continents drifted, once joined in a single supercontinent called Pangaea. He was mocked. No known force could move such massive slabs of land. But in the mid-20th century, oceanographers discovered spreading ridges on the seafloor and deep trenches where crust disappeared. Earth's crust, it turned out, was broken into enormous plates, carried by the slow convection of molten rock below. These tectonic plates push and pull, forming mountains, splitting oceans, and triggering earthquakes. What seemed static was alive with motion. The slow, ceaseless breath of our planet's surface reshaping itself across time. For most of history, lightning and thunder were seen as the anger of the gods. Before electricity was understood, a thunderstorm was pure mystery, light and sound unleashed from the heavens. People believed it was divine wrath, Zeus throwing bolts, Thor striking the sky with his hammer. The truth began to emerge in the 1700s, when Benjamin Franklin and others experimented with static charge. They found that lightning was an immense electrical discharge between clouds and the ground. Inside a storm, turbulent air drives ice and water droplets to collide billions of times, separating positive and negative charges until the imbalance becomes unbearable. The sky suddenly releases that energy in a bolt so hot, it turns the air into plasma. The air expands faster than sound, producing thunder, the echo of nature restoring balance. Lightning isn't divine fury, it's a glimpse of the atmosphere's invisible electricity, releasing energy that keeps Earth's weather in motion. No one knew how a snowflake could grow so perfectly symmetrical. Each snowflake, unique yet balanced, has fascinated observers for centuries. Early thinkers assumed they were simple, frozen raindrops. Then the invention of the microscope revealed something astonishing. Every snowflake shared the same six-sided symmetry, but no two were identical. The answer lies in water's molecular structure. Each water molecule connects to others at precise angles, forming hexagonal crystals when it freezes. As the crystal drifts through the sky, it passes through changing layers of humidity and temperature. Those subtle shifts alter the way water vapor collects along each branch, growing outward in mirrored patterns. The symmetry is built into the geometry of hydrogen and oxygen, while the endless variations come from chaos in the clouds. Every snowflake is a frozen record of the air it fell through, a microscopic masterpiece sculpted by physics, temperature, and time. The question of why the sky is blue baffled scientists for generations. For centuries, even the simplest sight above us, the color of the sky, remained unexplained. Many thought the air reflected the ocean below. Others believed blue light leaked through cracks in the heavens. The real answer arrived in the 19th century with the work of physicist Lord Rayleigh. Sunlight contains every color, but the atmosphere doesn't treat them equally. As light travels through air, molecules scatter shorter wavelengths, the blues and violets, far more than the longer reds. Our eyes are more sensitive to blue, so that color dominates. At sunrise and sunset, sunlight travels through a thicker layer of air, scattering away the blues and leaving the warm hues that paint the horizon. The sky's color is not illusion or reflection, it's light itself, divided and scattered by the air we breathe. For ages, no one could explain what caused disease to spread through cities. When plagues swept through towns, people had no idea what invisible force carried them. Theories blamed bad air, curses, or divine punishment. It wasn't until the 19th century that the mystery broke open. Doctors like Ignaz Semmelweis noticed that when hands were washed between patients, death rates fell. Louis Pasteur proved that microbes, living organisms too small to see, could spoil food and cause infection. Robert Koch went further, identifying specific bacteria responsible for deadly diseases. Under the microscope, an unseen world appeared. Billions of tiny creatures thriving in water, air, and on the human body. Once the invisible culprits were known, medicine transformed. Sanitation, sterilization, and vaccination turned chaos into prevention. The discovery of germs changed everything about how we live, turning superstition into science and saving countless lives. People once wondered how birds could possibly navigate thousands of miles without getting lost. Every year, migratory birds travel from one hemisphere to another, crossing entire oceans and returning to the same patch of forest or shore. No compass, no map, yet perfect precision. For centuries, it seemed impossible. In the 20th century, scientists discovered that birds navigate using a combination of senses. They can read the position of the sun, track the stars, and even detect polarized light invisible to humans. More astonishingly, many species sense the Earth's magnetic field through specialized cells containing microscopic crystals of magnetite, effectively giving them a biological compass. They memorize landmarks, wind patterns, and even smells carried by the air. Their migrations are ancient, written into their genes through evolution. What looks like instinct is, in truth, the result of countless generations refining nature's most complex navigation system. The mystery of how the heart keeps beating on its own once seemed impossible to solve. Even centuries ago, doctors knew the heart was the engine of life. But how could it pulse endlessly without rest, or even continue beating after being removed from the body? Many believed it was powered by an invisible vital force. The truth was stranger and simpler. Deep inside the heart lies a network of electrical cells known as the cardiac conduction system. At its center, the sinoatrial node generates rhythmic electrical impulses, spreading through the heart's muscle fibers and triggering each contraction. The pattern is self-sustaining, regulated by chemical gradients across cell membranes. The brain can influence the pace, but it doesn't start the beat. The rhythm begins before birth and continues independently until death. The heart is an electrical instrument built from living tissue, conducting its own silent symphony every moment of our lives. For centuries, no one knew what made the northern lights dance across the night sky. The aurora once seemed like a miracle, shifting veils of green and violet light that rippled across polar skies. Early explorers wrote of spirits or fires beyond the horizon. It wasn't until the age of space exploration that scientists uncovered the truth. The sun constantly releases charged particles into space, forming the solar wind. When those particles reach Earth, our magnetic field guides them toward the poles, where they collide with atoms high in the atmosphere. Each collision excites the atoms, making them release photons of light. The colors depend on which gases are struck. Oxygen glows green, nitrogen pink or purple. The result is a luminous dialogue between our planet and its star, written in magnetism and air. The aurora is not magic, but understanding it only makes it more wondrous. A visible heartbeat of the solar wind flowing across the sky. The secret of how the Earth's oceans formed was once completely unknown. The early Earth was a fiery world of rock and gas, far too hot for liquid water. Yet billions of years later, blue oceans covered most of its surface. Where did all that water come from? For centuries, no one could agree. Some thought it rose from within Earth itself, released by volcanic eruptions. Others suspected it arrived from space. Evidence now shows that both are true. As the young planet cooled, steam trapped in its molten interior condensed into rain, filling the first basins. Later, icy asteroids and comets delivered more water, carrying hydrogen that matched the isotopic signature of Earth's seas today. Every drop in the ocean tells that story, forged in the collapse of distant stars, frozen in space, and finally delivered to a planet ready to cradle life. The oceans we know are ancient visitors, fallen from the sky and born from the deep earth alike. No one could explain why the moon always shows the same face. To sky watchers across centuries, the moon felt like a coin held perfectly still, one side forever turned toward us. Early explanations ranged from cosmic magnetism to some hidden tether. The real answer is tidal locking, a slow exchange of energy between two bodies joined by gravity. Long ago, the moon spun much faster. Earth's gravity raised subtle bulges in the moon's rock, just as it raises ocean tides here. Those bulges were pulled slightly off-center, and friction inside the moon acted like a brake, bleeding away rotational energy. Over immense time, the spin slowed until the moon's rotation period matched its orbital period. Now it turns once for every journey around Earth, keeping one hemisphere always in view and the far side perpetually hidden. The effect is common across the solar system. Many moons present a single face to their planets. What seems like stillness is really perfect synchronization, gravity's metronome keeping time. For a long time, the origin of earthquakes was a terrifying mystery. When the ground jolted without warning, people imagined monsters below, divine anger above, or hollow caverns collapsing in chains. The mystery only began to yield when scientists mapped where quakes happened, and noticed patterns tracing long belts around the globe. Those belts, we later learned, mark the edges of tectonic plates, immense slabs of crust floating atop slowly convecting mantle rock. Plates stick together at rough boundaries until stress accumulates beyond what the fault can bear. Then, in a sudden slip, elastic strain releases as seismic waves that ripple through rock and shake the surface. Different fault motions strike slip, normal, reverse, carve distinct signatures in the motion we feel. Aftershocks are the crust adjusting to its new shape. Even silent years are not calm stress is always building. Earthquakes are not omens, but the planet's mechanics at work, a living world creaking as it cools and reshapes itself from within. No one understood how coral reefs could grow in waters too poor to feed them. Warm tropical seas look pristine because they are low in nutrients, yet that is where coral reefs explode with life. The paradox confused early naturalists. The key is cooperation at microscopic scale. Inside each coral polyp live algae called zooxanthellae. With sunlight, these guests photosynthesize, turning carbon dioxide and water into sugars and oxygen that feed the coral. In return, the coral provides shelter and dissolved nutrients and recycles waste that the algae use again. Sponges, fish, worms, and crustaceans add more loops to the recycling chain, trapping and reusing scarce nutrients so efficiently that little is lost. Coral skeletons, built from calcium carbonate, create labyrinths that slow water, further concentrating resources. The reef becomes a city fueled by sunlight rather than fertilizer. A model of circular economy evolved over millions of years. In apparently barren seas, life prospers by sharing. Each species a conduit that keeps the energy flowing. For centuries, people had no idea where the wind came from. Invisible and powerful, wind filled sails and sculpted dunes, yet its source remained guesswork. The explanation arrives with uneven heating. The sun warms the equator more than the poles, land differently than ocean, and dark surfaces more than bright ones. Warm air expands and rises, lowering surface pressure. Cooler, denser air flows toward those lows, creating wind. Earth's rotation deflects moving air sideways, to the right in the northern hemisphere and to the left in the southern, a twist called the Coriolis effect. That deflection organizes the atmosphere into broad belts of trade winds, westerlies and polar easterlies. Mountains channel and lift air coastlines spawn sea breezes by day and land breezes by night. Storms deepen pressure contrasts and accelerate the flow. Wind is the atmosphere smoothing temperature and pressure differences, forever trying to balance the books of heat across a spinning, sunlit world. The strange stillness of space once raised a question: how does sound travel on Earth, but not in the void? On Earth, sound is vibration, passing from molecule to molecule, through air, water, or solid materials. Without a medium, there is nothing to carry the wave. Space is so sparse that those collisions rarely happen, so a shout on the moon would never reach another ear. That silence confused early thinkers who assumed the heavens must be filled with some ether carrying celestial sounds. Modern physics shows that while audible sound fails in vacuum, other waves thrive. Charged particles in space create ripples in magnetic fields and plasma that spacecraft detect as radio and plasma waves. When translated to audio, we can hear Jupiter's auroras or the hiss of the solar wind. Inside spacecraft or planetary atmospheres, sound returns. Mars carries thin, higher-pitched echoes, while Venus would transport sound efficiently through its dense air. Silence, then, is conditional. Space is quiet to our ears, but not to instruments tuned to light and fields. Before the age of chemistry, no one knew what fire really was. Fire looked like a fifth element, alive and hungry. An old theory claimed burning substances released an essence called phlogiston. The puzzle unraveled when careful weighing revealed that metals gained mass when they burned, contradicting the idea of something escaping. Antoine Lavoisier showed that combustion is a union with oxygen. Heat supplies the activation energy that lets fuel molecules break and reform bonds with oxygen, producing new molecules, typically carbon dioxide and water, and releasing stored chemical energy as heat and light. Flames are regions where countless reactions race forward at once. Color and temperature depend on which fragments glow and how hot they are. Extinguishers work by cooling the reaction, smothering oxygen, or separating fuel. What seemed mystical is controlled rearrangement at atomic scale. The same logic that powers metabolism in cells, only sped up and spilling its energy as visible, dancing light. The mystery of why ice floats instead of sinking confused early scientists. Water bends the usual rule. Most liquids become denser as they cool, and freeze water reaches maximum density just above freezing, then expands as it locks into ice. The reason is in hydrogen bonding. Each water molecule has a bent shape and partial charges that attract neighbors into a hexagonal lattice. That open framework spaces molecules farther apart than in liquid water, lowering density so ice rises to the top. The consequence is profound. Floating ice insulates lakes and seas, protecting liquid water beneath through winter, and stabilizing climates by reflecting sunlight. Aquatic life survives under an icy roof. Spring overturn renews nutrients as surface water warms and mixes. Even rock weathering and soil structure depend on water's expansion and contraction. A small molecular quirk becomes a planetary safety feature, cushioning ecosystems and moderating temperatures across the world. For ages, no one could explain what causes tides to rise and fall. Sailors timed voyages by the breathing of harbors, but the cause seemed capricious. The pattern follows gravity's geometry. The moon's pull is strongest on the near side of Earth and weakest on the far side, stretching the oceans into two bulges. As Earth spins, coastlines rotate through these bulges, producing two high tides most days. The sun adds its own tug. When sun, moon, and Earth align during new and full phases, tides intensify into spring tides when they form right angles at quarter phases. Tides soften into neap tides. Ocean depth, basin shape, and local resonance tune the timing and height, creating famous exaggerations in some inlets and subtle swells in others. Tides are not mysterious sloshing, but precise, predictable choreography. Celestial mechanics written in water, keeping time with the dance of Earth and Moon. The reason some volcanoes sleep for centuries and then awaken suddenly was once unknown. Villages could thrive for generations beneath a quiet cone, only to face a sudden, devastating eruption. The trigger lies in magma's slow, hidden evolution. Deep underground, molten rock, rich in dissolved gases, accumulates in chambers. As crystals grow, they change the melt's chemistry, often making it stickier and better at trapping gas. New injections of hotter magma can reheat the system, increase pressure, and fracture surrounding rock. When the overlying cap fails, gas expands violently, blasting ash and pumice skyward and sending pyroclastic flows racing down slopes. Other times, logas basalt simply pours out in fluid fountains. Monitoring ground swelling, heat, micro-earthquakes, and gas composition now reveals the prelude to many eruptions. The schedule remains irregular, but the process is clear. Volcanoes are pressure cookers connected to Earth's interior, releasing heat in pulses that mark the planet's long cooling. The source of the Earth's magnetic field was one of geology's great puzzles. A compass needle's steady northward turn needed an explanation more robust than legends of a polar mountain of iron. The breakthrough came from viewing Earth as an electrical generator. Beneath the rocky mantle lies a liquid outer core of iron alloy, swirling around a solid inner core. Convection driven by heat loss and crystallization organizes flows. Earth's rotation adds a twist, helping coherent spirals form. Moving conductive metal creates electric currents, and those currents sustain a global magnetic field, a self-exciting dynamo. The field is not fixed. It drifts, weakens, strengthens, and occasionally flips, leaving magnetic stripes on growing ocean crust that record past reversals, like tree rings. This invisible shield deflects much of the solar wind, shepherding charged particles toward the poles and protecting the atmosphere. A simple needle aligns because deep inside, a metallic ocean is in motion, powering a planet-scale force. No one knew how plants turned sunlight into life. Plants seemed to pull nourishment from soil and water alone, until careful experiments showed they also release oxygen in light. Inside green chloroplasts, arrays of pigments capture photons. That energy frees electrons from water, producing oxygen and driving an electron transport chain that charges cellular batteries. The resulting energy and reducing power feed the Calvin cycle, stitching carbon dioxide into sugars that fuel growth, build wood, and seed entire food webs. Even the air we breathe is a byproduct of this solar chemistry. Algae in the oceans and forests on land together manufacture the planet's oxygen and much of its organic matter. Photosynthesis is not just a plant trick, it is the root of almost every meal and breath. Light becomes living structure, and nearly every creature traces its energy back to those ancient green engines humming quietly in leaf and wave. For centuries, the reason leaves change color in autumn remained a mystery. People tied the colors to frost or imagined sap turning to pigment, but the process is a planned retreat. As days shorten and nights cool, trees prepare for winter by reclaiming valuable nutrients from leaves. The veins seal, and chlorophyll, the dominant green pigment, breaks down first, revealing yellows and oranges from carotenoids that were there all along. In some species, leftover sugars spur the creation of anthocyanins, which glow red and purple and may protect leaves from sun or pests during the final withdrawal. When the job is done, a layer of cells detaches the leaf cleanly, and it falls. The flare of autumn is not decay, but efficiency made visible, a brief unveiling of hidden colors as trees pack away resources for the next burst of spring. The question of how a caterpillar becomes a butterfly once seemed like pure magic. From a crawling leaf eater to a flying nectar sipper, the change looked total. Inside the chrysalis, enzymes dissolve much of the caterpillar into a nutrient soup, but tucked within are imaginal discs, quiet cell clusters already coded for wings, legs, eyes, and antennae. Fed by the released nutrients, these discs proliferate and differentiate, guided by precise genetic programs and pulses of hormones. Neurons rewire, muscles reform, and a new digestive system suited to a different diet takes shape. The result is not a resurrection, but a rebuild, reusing parts and plans in a different configuration. Metamorphosis is evolution's remodeling genius, allowing one genome to inhabit two lives, optimized for different tasks, growth and dispersal. What looks like disappearance is actually construction, hidden behind a thin wall of silk and patience. For a long time, no one could explain what caused pearls to form inside oysters. Legends spoke of moonlight or tears trapped by the sea. The reality is biological craftsmanship born of self-defense. When a parasite or grit intrudes into the soft mantle, the mollusk isolates the irritant by laying down layers of nacre, microscopic tiles of calcium carbonate, glued with proteins. The layering creates interference effects that give pearls their depth and luster. Over years, the sphere grows more perfect as the animal adds thousands of ultra-thin coats. People learn to encourage this process by inserting tiny beads or tissue, letting the oyster continue its careful work. Each pearl's color and sheen record the species, the water, and the pace of deposition. A gem, then, is an autobiography of irritation transformed, patient geology performed by an animal one layer at a time. The way bats find their way in total darkness baffled early naturalists. They flew through cave mazes and midnight forests without striking branches, suggesting mysterious senses. Careful experiments revealed echolocation. Bats emit rapid, high-frequency calls and analyze echoes to map their world. Timing reveals distance, frequency shifts reveal speed. Subtle changes encode texture and shape. Muscles in the middle ear protect hearing during call emission and relax to capture faint returning echoes. Some bats alternate frequencies to avoid interference. The system is so refined that a bat can detect a thread and pursue insects weaving unpredictable paths. Different species tune their sonar for open skies, cluttered foliage, or water surfaces, demonstrating evolution's ability to tailor the same principle to many niches. Seeing by sound turns the night into a readable landscape, rich as daylight to those equipped to hear it. No one understood how whales could communicate across entire oceans. Mariners heard ghostly moans through wooden hulls without knowing their source. Hydrophones later revealed a world of sound far below the waves. Water carries pressure waves efficiently, and at certain depths and temperatures, a sound channel bends low-frequency calls over vast distances. Baleen whales craft songs that can travel for hundreds or even thousands of kilometers, encoding identity, season, and perhaps location. Toothed whales use rapid clicks for echolocation and for social chatter within pods. Cultural transmission appears in some species. Songs evolve over years and spread across populations like trends. The sea is not silent. It is woven with voices adapted to the medium, messages carried by physics long before humans built radios. For centuries, the glow of fireflies was thought to be supernatural. A tiny lantern in a summer field invites stories. The science is elegant. A molecule called luciferin reacts with oxygen in the presence of an enzyme, luciferase, and a bit of cellular energy, releasing photons with remarkable efficiency. Almost all the energy becomes light. Fireflies control the timing by regulating oxygen flow to light-producing cells, creating coded flashes that differ by species and even by sex. Predators learn to read those signals, some mimic them to lure meals. The color and brightness shift with chemistry and temperature, a living lamp tuned to the night. Bioluminescence evolved repeatedly across life, but the firefly's version is a masterclass in signaling, a conversation between individuals made visible in the dark. The mystery of how fish breathe underwater puzzled philosophers for millennia. Breathing in water seems impossible until you examine a gill. Water flows across thin, feathery filaments laced with capillaries. Oxygen molecules diffuse from water, where their concentration is higher, into blood, while carbon dioxide diffuses out. A clever countercurrent arrangement sends blood in the opposite direction of the water, keeping the gradient steep along the entire length, maximizing extraction. Hemoglobin binds the captured oxygen and delivers it to tissues just as in land animals. Different fish tailor gills to lifestyles. Fast swimmers build vast surface area, bottom dwellers economize. Some species supplement with lung-like structures for stagnant waters. What appears effortless is a triumph of surface area and flow control, turning a sparse resource into enough breath to fuel motion in a dense, drag-filled world. No one could explain how spiders spin silk stronger than steel. Threads that look delicate hold prey, bridge gaps, and even catch seeds on the wind. Silk's strength comes from its hierarchical design. Within a spider's silk glands, liquid proteins align as they are drawn through narrowing ducts. Shear forces and chemistry coax the proteins into nanocrystals connected by stretchy, amorphous regions. The crystals give strength, the flexible links give toughness. By adjusting draw speed and mixing secretions, a spider produces different silks, rigid drag lines, sticky snares, soft egg sacs. Humidity and temperature fine-tune performance after the strand leaves the body. Engineers try to copy this process, but the spider's on-demand spinning remains unmatched. What the eye sees as a fragile thread is sophisticated composite engineering written into a molecule and woven at room temperature. For ages, the flight of birds seemed to defy every rule of physics. Wings turned muscle into lift with a grace that mocked human attempts. The physics is now clear. A wing's shape speeds airflow over the top, lowering pressure and creating upward lift, while adjustable feathers manage vortices and store. The downstroke supplies thrust, the upstroke is cleverly rotated to minimize drag. Hollow bones, anchored flight muscles, and a one-way airflow through efficient lungs supply power without overheating. Birds tweak wind loading and aspect ratio for their niches. Albatrosses trade maneuvering for effortless gliding. Hawks balance soaring and agility. Hummingbirds hover by reversing tiny wing strokes at dazzling glare. Speed. What looked like defiance is optimization. Evolution discovering many solutions to the same equations of air and motion, written in feather and bone. The strange behavior of magnets fascinated humans long before we understood electricity. Magnets seemed alive, invisible forces tugging at metal, pulling and repelling with no touch at all. Ancient Greeks discovered lodestones that could attract iron, but the reason was unknown. For centuries, this strange power was treated as natural magic. In the 19th century, Hans Christian Ørsted noticed that an electric current made a compass needle twist, revealing that electricity and magnetism were linked. James Clerk Maxwell later unified them mathematically, showing that changing electric fields create magnetic fields, and vice versa, two halves of one elegant phenomenon. Even light, he realized, is an electromagnetic wave rippling through space. The magnet on a refrigerator, the compass guiding a ship, the signals traveling through every wire, they're all part of the same cosmic dance of moving charges. Magnetism isn't sorcery. It's one of nature's fundamental conversations, silent and unseen, shaping every atom, every planet, every spark of light itself. No one knew why salt could melt ice. For most of history, salt's power to clear frozen roads or thaw fish seemed miraculous. When salt touches ice, it dissolves into sodium and chloride ions that disrupt the hydrogen bonds between water molecules. Ice normally forms when water reaches 0 degrees Celsius, but the ions make it harder for molecules to lock into that neat crystalline structure. This lowers the freezing point, meaning the ice melts even when the temperature is still below 0. The melting absorbs heat from its surroundings, so the process feels cold even as it liquefies the ice. This principle, freezing point depression, also explains how antifreeze protects car engines and why seawater freezes at a lower temperature than fresh water. What seems simple is really a subtle interplay between order and chaos, with salt acting as a tiny saboteur in water's perfect geometry, undoing solidness itself one bond at a time. For centuries, the reason some metals rusted while others did not was unclear. Iron left outdoors slowly transformed into reddish flakes that spread and crumbled, while silver and gold stayed bright for generations. Alchemists believed rust was the metal's spirit leaving its body. In truth, it's chemistry at work, oxidation. When water and oxygen contact iron, atoms at the surface give up electrons to form iron ions, which combine with oxygen and water to produce hydrated iron oxide, rust. The process feeds on itself. Each new flake exposes fresh metal beneath. Some metals, like aluminum and stainless steel, resist corrosion because they form an invisible oxide layer that clings tightly, sealing the surface from further attack. Rust is slow combustion, a silent mirror of fire. It consumes energy stored in the metal, turning it back toward its more stable mineral form. Even our strongest creations eventually yield to oxygen, the most patient sculptor on Earth. Before chemistry was born, the transformation of matter in reactions looked like alchemy. Early experimenters watched metals dissolve in acids or liquids bubble and change color without understanding what truly happened. They believed materials contained hidden essences that could be released or purified through ritual. The turning point came in the 18th century, when careful measurements revealed that matter isn't created or destroyed in reactions, only rearranged. Lavoisier's law of conservation of mass proved that burning, rusting, and fermenting were different forms of the same process, atoms trading partners. Later, Dalton's atomic theory explained that every element is made of identical units, and reactions simply rearrange those building blocks. The transmutations of alchemy were replaced by chemistry's precise balances of energy and structure. And yet, in a poetic twist, nuclear physics eventually achieved true transmutation, changing one element into another. What was once mysticism became mathematics, revealing that the alchemists were wrong about process, but right about possibility. The mystery of what causes lightning to strike twice in the same place puzzled early scientists. People once said lightning never struck the same spot twice, a comforting myth born from fear. But tall trees, steeples, and skyscrapers often endure repeated strikes because lightning obeys physics, not fairness. Inside a thundercloud, collisions between ice particles separate charges, positive near the top, negative near the bottom. The electric potential builds until the air itself breaks down, forming a jagged path called a stepped leader. When it connects to an opposite charge on the ground, a powerful current surges upward, the flash we see. If the storm persists, the same conductive path can trigger new strikes seconds later. Lightning rods work by giving that energy a safe route to Earth. Each bolt is electricity restoring balance between sky and ground, and its repetition isn't vengeance or coincidence, just the same invisible tension finding the easiest way home again. For ages, no one understood what made glass transparent. To ancient artisans, glass was a miracle. Sand that melted into stone clear as air. They could shape it, color it, polish it, but not explain its see-through nature. The secret lies in its atomic disorder. In crystals, atoms line up in neat, repeating grids that scatter certain wavelengths of light. Glass, however, is a frozen liquid. Its atoms are locked in random positions. That irregularity leaves no energy levels available for visible light to excite, so photons pass through unabsorbed. In other words, the material simply doesn't interact with the colors we can see. Light slows as it travels through, bending slightly at boundaries, the reason lenses focus images. Transparency isn't purity or emptiness. It's the quiet consequence of chaos. A window pane is a solid that forgot how to crystallize, a liquid caught in mid-flow, forever still and perfectly clear. The secret behind rainbows was once one of nature's most charming riddles. To ancient eyes, the rainbow was divine, a bridge to heaven, an omen, or a promise. For centuries, its curved shape and vivid colors remained unexplained. The solution appeared through experiments with prisms. Sunlight, though white, is a blend of many wavelengths. When it enters a raindrop, it slows and bends refraction, and part of it reflects off the back of the droplet. As it exits, each color bends by a slightly different amount, spreading into a spectrum. Red bends least, violet most, creating the familiar order we see. Every observer sees their own rainbow, built from countless droplets reflecting light at just the right angle. A secondary, fainter arc appears when light bounces twice inside the droplet, reversing the colors. What we call a rainbow is not an object, but geometry, sunlight, water, and perception meeting for a moment in the air. No one knew why some substances glow after being exposed to light. Long before glow-in-the-dark toys or watch dials, people marveled at minerals that shone softly after nightfall. The phenomenon, called phosphorescence, baffled natural philosophers. When light strikes certain materials, it lifts electrons to higher energy levels. In most, those electrons fall back instantly, emitting light as fluorescence. But in phosphorescent materials, defects or impurities trap electrons in metastable states, tiny pockets of delay. The electrons release their energy slowly, sometimes over hours, creating that gentle afterglow. It's light postponed, energy stored and released at leisure. Today, phosphorescent compounds mark emergency exits, track radiation, and illuminate the deep sea. The faint glow that once seemed supernatural is quantum patience, matter holding onto sunlight and letting it go in whispers instead of flashes, a lingering memory of brightness in the dark. The way sound echoes through valleys and caves once seemed like the voice of spirits. Before acoustics, echoes were eerie, unseen presences replying in perfect imitation. The explanation is simple but beautiful. Sound is vibration moving through air. When those waves hit a hard surface, rock, wall, or water, they bounce back. If the returning sound reaches your ear more than about 1/10 of a second after the original, you hear it as a distinct echo. Shorter delays blend into reverberation, creating that rich tone in cathedrals and halls. The strength and clarity depend on distance and texture. Smooth stone reflects forests absorb. In vast canyons, multiple echoes overlap, turning a single shout into a chorus. Bats, whales, and submarines use this same principle to navigate by sound. What once seemed supernatural is simply the air's memory of noise, a conversation between space, motion, and time. For a long time, the movement of planets across the night sky defied every simple explanation. To ancient astronomers, the wandering stars traced loops and reversals across the heavens, breaking the perfection of celestial order. The Earth-centered model required elaborate epicycles to explain these paths. Then, in the 16th century, Copernicus proposed that the Sun was the true center. The apparent backward motion, retrograde, occurs when Earth, moving faster on its inner orbit, overtakes another planet, making it seem to drift backward against the stars. Galileo's telescope confirmed this new reality. Jupiter had moons, Venus showed phases, and the heavens were not unchanging. Kepler refined the picture, showing that orbits are ellipses, and Newton revealed gravity as the force behind them all. The dance of the planets, once a mystery of divine mechanics, turned out to be pure geometry, a clockwork universe turning gracefully under the pull of invisible law. The idea that stars could be suns, was once almost unthinkable. For thousands of years, humanity saw the sun as singular, a fiery god among distant candles. The stars were thought to be holes in the heavens, or crystals reflecting divine light. It wasn't until the 16th century that thinkers like Giordano Bruno proposed that each star might be a sun of its own, with worlds orbiting around it. The claim was heretical, but telescopes later proved him right. Spectroscopy showed that starlight contains the same elements as the sun: hydrogen, helium, calcium, iron. The difference is only distance. Every pinprick in the night is a blazing sphere of plasma, fusing hydrogen into helium, shining for billions of years. Some are far larger or smaller than our own. The realization transformed the sky from a ceiling into a cosmos, a universe not of lights, but of suns, each with its own potential for life. For centuries, no one knew what held the planets in orbit. The celestial spheres of antiquity turned smoothly in their imagined shells. Even after Copernicus placed the sun at the center, the cause of motion remained unknown. Isaac Newton solved it by recognizing that the same force pulling an apple to Earth also keeps the moon aloft. Every mass attracts every other mass, and that mutual attraction, gravity, governs the entire cosmos. A planet is constantly falling toward the sun, but moving sideways fast enough to keep missing it, tracing a stable orbit. Newton's equations could predict eclipses, tides, and even the paths of comets. 2 centuries later, Einstein deepened the picture. Gravity isn't a force, but the curvature of space-time around massive objects. Planets follow the natural curves of that geometry. What we feel as weight is really the shape of the universe, gently guiding us through its folds. The source of comets and their glowing tails was long misunderstood. For much of history, comets were seen as omens, blazing swords or heavenly messengers. Their unpredictable arrivals terrified kings and inspired myths. The truth emerged when astronomers realized that comets followed repeatable orbits. Edmond Halley calculated that one comet returned every 76 years, proving they were not atmospheric phenomena, but solar system travelers. Comets are icy relics from the solar system's birth, preserved in distant reservoirs like the Kuiper Belt and Oort cloud. As they approach the sun, heat vaporizes their frozen surfaces, releasing dust and gas that form glowing tails blown outward by solar wind. Each pass reshapes them, and when Earth crosses their trails, we see meteor showers. What once seemed divine wrath is now cosmic memory, fragments of creation still wandering through the light of the same star that made them. No one could explain why some stars twinkle while others do not. To the naked eye, stars shimmer and dance while planets glow steadily. For centuries, people thought stars themselves flickered. The truth lies in Earth's atmosphere. Starlight travels through space perfectly straight, but when it reaches our turbulent air, it bends and refracts through layers of different temperatures and densities. Those tiny, random shifts cause the light to change direction and brightness many times a second, producing the familiar sparkle. Planets, being closer, appear as small disks rather than points, so their fluctuations average out. Above the atmosphere, as astronauts know, stars don't twinkle at all. They burn with steady brilliance. The shimmering of the stars is not their doing, but ours, a fragile veil of moving air turning distant suns into trembling jewels across the night sky. The nature of the Milky Way was a mystery until the telescope revealed its truth. To the naked eye, the Milky Way looked like spilled milk, a luminous river arching across the heavens. Poets imagined it as divine residue, philosophers as mist. Then Galileo pointed his telescope toward it in 1614 and saw that it resolved into innumerable stars. The haze was an illusion, created by distance and quantity. Centuries later, astronomers mapped the structure and realized we live inside a vast spiral galaxy, one among billions. Our Sun is a single star, orbiting the galactic center every 200 million years. The pale band that crosses the sky is our Eon view through its crowded plain of stars, dust, and nebulae. What once seemed a gentle glow is a panorama of suns so dense that their light merges into one continuous shimmer, the collective radiance of our galactic home. For ages, people wondered what powered the shimmering bands of Saturn's rings. When Galileo first saw Saturn through his small telescope, he thought the planet had ears. Later, higher magnification revealed thin, delicate rings encircling it, structures so perfect they seemed solid. For centuries, no one knew what they were. Modern science shows that Saturn's rings are made of countless icy particles ranging from dust grains to mountain-sized chunks, orbiting in near-perfect balance. Their brightness comes from sunlight reflecting off ice, and their gaps are sculpted by the gravity of Saturn's moons. Collisions keep the particles ground to powder, maintaining the ring's sharp edges. They're not eternal. Over millions of years, much of the material will spiral inward or drift away. The rings are a transient halo, frozen music in motion, the remains of a shattered moon or captured comet, spread thin around one of nature's most beautiful balancing acts. No one knew what caused solar eclipses or why the sun would vanish from the sky. To ancient peoples, a solar eclipse was terrifying. The sun swallowed, the day undone. Some believed dragons devoured it, others that gods quarreled in the heavens. Only careful observation revealed the pattern. Eclipses occur when the moon passes directly between Earth and the sun, casting its shadow across the planet. The alignment happens because the sun and moon appear nearly the same size in our sky, though the sun is 400 times larger and 400 times farther away. Totality is fleeting, lasting only minutes. But during it, the sun's corona blazes into view, a halo of plasma streaming millions of kilometers into space. Once a sign of doom, eclipses are now tools of discovery, helping reveal the sun's outer layers and test Einstein's theories. What once symbolized darkness now illuminates understanding. The secret behind the moon's phases once inspired myths instead of science. Many cultures believed the moon waxed and waned by choice, dying and reborn each month, or devoured by spirits and renewed. The real cause is geometry. As the moon orbits Earth, half its surface is always lit by the sun, but from our perspective, we see different portions of that illuminated half. When the moon lies between Earth and sun, its bright side faces away from us, the new moon. As it moves around us, more of that half becomes visible, reaching fullness when Earth sits between the two. The cycle repeats every 29.5 days. Its rhythm has guided calendars, crops, and rituals for millennia. The changing moon isn't a transformation, but a perspective, a reminder that what we see depends not only on light, but on where we stand within it. For centuries, the origin of meteorites was unknown. Stones from the sky seemed impossible. When rocks fell from the heavens, people thought they were hurled by storms or volcanoes. The idea that stones could come from space was dismissed as folklore. In the early 19th century, chemical analyses and witnessed falls proved otherwise. Meteorites are fragments of asteroids, the Moon, or even Mars, hurled into space by impacts and drawn to Earth by gravity. As they plunge through the atmosphere, friction heats them to thousands of degrees, creating the streaks of light we call meteors. Most burn up entirely, but a few survive the fall. Their isotopes reveal the age of the solar system over 4.5 billion years, making them the oldest physical objects we can touch. Once seen as omens, they're now evidence, pieces of planetary building blocks still visiting the world they never quite became. The reason the night sky is dark, even with countless stars, baffled astronomers for generations. If the universe were infinite and eternal, every line of sight should end on a star, and the sky should blaze with light. If it doesn't. This puzzle, called Olber's paradox, endured until the discovery that the universe had a beginning and is expanding. The light from distant galaxies is stretched into infrared and microwave wavelengths invisible to the eye, and the most distant starlight hasn't had time to reach us yet. The darkness overhead isn't emptiness, but evidence, a shadow cast by time and growth. The faint glow of the cosmic microwave background, the afterglow of the Big Bang, still fills space, though our eyes can't see it. Night isn't the absence of stars. It's the unfinished story of light still traveling, still unfolding, across a universe too young for its own brilliance to fill every corner. No one understood how fossils formed and turned to stone. When people first found seashells on mountain peaks, they imagined they were left behind by ancient floods or playful gods. The idea that living things could slowly become rock seemed impossible. The answer lay in deep time. When a creature dies and is buried under sediment, its soft tissues decay, but its bones and shells can be replaced molecule by molecule with minerals carried by groundwater. Over thousands or millions of years, the original material is transformed, not destroyed, but transmuted into stone. Sometimes, only impressions remain, the faint outline of a leaf, or the ripple of a fish's fin pressed into ancient mud. Fossils capture moments life once lived and time erased. They are Earth's diary pages, written not in ink, but in quartz and limestone, preserving the whispers of creatures long vanished, yet still reaching across epochs to be seen. For ages, the shape of the Earth itself was debated fiercely. To early eyes, the world felt flat. The horizon stretched endlessly, and anything beyond it was mystery. Ancient sailors noticed that ships vanished hull first as they sailed away, and that new stars appeared as one traveled south, subtle hints that the world curved. The Greek philosopher Eratosthenes measured its circumference more than 2,000 years ago, using shadows and geometry. Yet myths of flatness persisted, shaped by culture and fear of the unknown. It took circumnavigation, photographs from orbit, and astronauts' first-hand accounts to make the truth undeniable. Earth is a sphere, slightly flattened at the poles by its spin. What once divided thinkers, flat or round, stable or infinite, has become a symbol of unity. We all share one small, spinning world, balanced between light and darkness, floating in space yet bound together by its gentle curve. Before we found bacteria, the cause of food spoilage was a mystery. For centuries, people noticed that food left out would sour, rot, or grow mold, but no one knew why. Some believed decay was spontaneous, that life emerged from non-living matter. It wasn't until the 17th century, when Antony van Leeuwenhoek peered through his handmade microscope, that anyone saw the tiny organisms responsible. Later, Louis Pasteur's experiments proved that microbes were everywhere, floating in the air, waiting for nutrients. They were not spirits or vapors, but living cells multiplying invisibly. Pasteur's work gave birth to germ theory, refrigeration, and sterilization, the very foundations of modern hygiene and medicine. The mystery of rot became the science of life itself. Those invisible agents, once seen as destroyers, turned out to be essential to digestion, fermentation, and the balance of every ecosystem on Earth. No one knew why some people could see colors others could not. To early observers, color blindness was a strange condition, unexplainable and often unnoticed. The discovery came from personal experience in 1794. Scientist John Dalton realized he couldn't distinguish red from green. His study led to the first scientific description of color vision deficiency. We now know that color perception depends on 3 kinds of cone cells in the retina, each sensitive to different wavelengths of light. Most people have all 3, but a genetic variation on the X chromosome can alter or remove one type, reducing the range of colors seen. Because the gene is carried on the X chromosome, the condition is far more common in men than in women. Color blindness isn't darkness. It's a different mapping of light. It reminds us that perception isn't absolute. It's biology's version of interpretation, painting the world through inherited filters of sight. For centuries, the mystery of sleep haunted philosophers and doctors alike. Why we spend a third of our lives unconscious baffled the ancient world. Some thought sleep was a cooling of the body, others that it was the soul's nightly voyage into another realm. Only with modern neuroscience did the truth begin to unfold. Sleep isn't a shutdown, but a dynamic process. Cycles of electrical rhythms sweeping through the brain. During deep sleep, the body repairs itself and consolidates memory. During rapid eye movement sleep, the mind rehearses and processes emotion. Deprived of it, we unravel, thought blurs, mood fractures, and health declines. Sleep restores order to the chaos of waking life. It's not idleness, but renewal, a nightly cleansing that resets the circuits of mind and body. Far from being mysterious nothingness, sleep is nature's most intimate form of maintenance, a quiet dialogue between consciousness and the need to rest. No one could explain what dreams were or why we have them. To ancient cultures, dreams were prophecies or messages from gods. Later, they were seen as random nonsense, the mind's idle chatter. But science revealed that dreaming is both structured and meaningful. During REM sleep, the brain becomes almost as active as when awake. Memories replay, emotions resurface, and neural circuits strengthen connections. The visual and emotional centers light up, while the logic centers quiet down, creating the strange, fluid narratives of dreams. They may help us process fear, practice survival, or solve problems unconsciously. Even nightmares serve a purpose, rehearsing threat in a safe environment. While Freud imagined dreams as hidden desires, modern neuroscience sees them as mental maintenance, the brain sorting its experiences into coherence. Dreams are the mind's nocturnal experiment, blurring the line between memory and imagination as we drift through the landscapes we build within. The question of why we age has fascinated humanity since ancient times. For most of history, aging was treated as fate, a slow decline written into the soul. Modern biology uncovered a more complex story. Every cell carries instructions for repair, but with each division, DNA accumulates tiny errors. Telomeres, the protective caps at the ends of chromosomes, shorten over time, eventually halting replication. Mitochondria lose efficiency, proteins misfold, and oxidative stress damages tissues. Aging is not one process, but many small failures of maintenance. Yet evolution allows it, because reproduction and survival of the young take precedence. Research now explores ways to slow those failures, from caloric restriction to gene repair, hinting that the line between aging and disease may blur. We age not by design, but by trade-off. Nature's compromise between growth and decay, between the urgency of life and the patience of time. For ages, the reason blood circulates through the body remained unknown. For millennia, physicians followed Aristotle's belief that blood ebbed and flowed like tides within the body. The Roman Dr. Galen imagined it was created in the liver, consumed by the organs and renewed endlessly. It wasn't until the 17th century that William Harvey proposed a radical idea. Blood moves in a continuous loop, driven by the pumping of the heart. He proved it through meticulous dissection and measurement, demonstrating that the volume of blood pumped in an hour exceeded the body's total supply. It had to circulate. His discovery transformed medicine, revealing the body as a system, not a collection of parts. Every heartbeat is a pulse of physics and biology entwined, sending life through miles of vessels. What once seemed mystical became measurable, and the rhythm of the heart became the proof of motion itself. The cause of fevers was once blamed on spirits or bad air. Long before germs were known, fevers were thought to arise from imbalance, excess bile, miasma, or punishment from the gods. Treatments ranged from bloodletting to burning herbs to drive out invisible forces. The truth emerged slowly. Fever is not the disease but the body's response to it. A defense mechanism evolved to help fight infection. When immune cells detect pathogens, they release chemical signals that raise the body's thermostat, making conditions less favorable for invading microbes and enhancing immune function. Though uncomfortable, fever is often beneficial, a signal that the body is actively battling invaders. Understanding this shifted medicine from superstition to physiology. The heat that once frightened us turned out to be our own weapon, warmth as warfare, a carefully tuned fire of survival. No one knew what made people sneeze or why it felt impossible to stop. Sneezing once carried superstition, a sign of divine favor or danger, prompting blessings like, "God bless you." The reflex, though, is pure physiology. When dust, pollen, or infection irritates the nasal lining, sensory nerves send a rapid signal to the brainstem. In an instant, the diaphragm, chest, and throat contract in a coordinated burst, expelling air at speeds over 100 miles per hour. The force clears irritants from the nose and upper airways, protecting delicate tissues. Even bright light can trigger a sneeze in some people, a quirk called the photic reflex. The sudden relief that follows comes from pressure release and restored airflow. Sneezing isn't a curse or omen, it's the body's defensive explosion, a perfectly timed storm of muscle, nerve, and air working together to keep our breath clean. For centuries, the pattern of inheritance in families was unexplained. Families noticed that traits echoed through generations, eye color, dimples, or disease, but no one knew how or why. Many believed characteristics blended like paints or were shaped by nurture alone. The mystery unraveled in a monastery garden, where Gregor Mendel spent years breeding pea plants. He discovered that traits followed predictable mathematical ratios, governed by discrete factors we now call genes. Each parent contributes one copy, and dominant and recessive relationships determine expression. His work lay unnoticed for decades, until rediscovered in the 20th century and confirmed by the discovery of DNA. What once seemed random became code. The laws of inheritance revealed that biology writes its own equations, carried quietly in every cell, a logic of life invisible to the eye, yet present in every generation that follows. No one could explain how a single cell could grow into a complex organism. The earliest microscopes showed that life begins as a tiny cell, but how that cell becomes a body remained a mystery. Inside that cell lies a complete set of genetic instructions, a molecular symphony waiting to unfold. As it divides, chemical gradients and genetic signals guide cells to specialize, some forming skin, others muscle, bone, or brain. The choreography is astonishingly precise. Cells communicate, move, and self-organize into tissues and organs without any central command. It's biology's greatest act of emergence, complexity rising from simplicity through feedback and timing. What once seemed miraculous now reads like a carefully tuned conversation between chemistry and code. Every human, every creature, begins as a single spark that divides and differentiates until it becomes consciousness itself, wrapped in flesh. Before genetics, the concept of heredity was pure mystery. People saw resemblance but had no model to explain it. Some believed traits came from blood, others from the blending of essences between parents. The turning point came with the understanding that information could be stored in matter itself. When scientists isolated DNA, they found a code made from 4 chemical letters: adenine, thymine, cytosine, and guanine, arranged in sequences that define every protein in the body. That code can copy itself with extraordinary fidelity, yet allows occasional mutations, fueling evolution. Heredity is not spirit or fate, but chemistry repeating with purpose. The double helix is both archive and algorithm, a molecule that remembers how to build a body and quietly passes that knowledge forward. Every living thing is part of that long, unbroken transmission of coded memory. No one knew what caused identical twins to form. For most of history, twins were seen as omens, blessings, or curses, 2 souls sharing one destiny. The biological explanation arrived with embryology. Identical twins begin when a single fertilized egg, containing one complete set of DNA, splits into 2 embryos early in development. Each half continues growing independently, sharing the same genetic blueprint. Fraternal twins, by contrast, form when 2 separate eggs are fertilized by 2 sperm at the same time. Identical twins are nature's perfect experiment in genetics, nearly identical DNA, yet shaped into distinct individuals by environment and experience. Studies of twins helped uncover the balance between nature and nurture, revealing how much of who we are is inherited and how much is learned. What once seemed mystical, 2 lives from one beginning, became a window into the workings of heredity itself. For ages, the structure of the atom was hidden from human understanding. Matter appeared continuous, a smooth, solid substance. Philosophers like Democritus imagined atoms as indivisible specks, but proof eluded them for millennia. In the 19th century, experiments revealed that atoms contained substructure. J.J. Thomson discovered the electron. Rutherford showed that atoms have a tiny, dense nucleus, and Bohr mapped their orbits like miniature solar systems. Quantum mechanics later replaced orbits with probability clouds, revealing electrons as both particles and waves. The atom turned out to be mostly empty space, a vast void with energy fields holding everything together. Within that emptiness lies nearly all the universe's matter and every chemical property we know. The invisible grain that shapes the world is not static, but a blur of motion, a paradox of emptiness holding substance in place. The question of what light actually is puzzled the greatest minds in history. Light was once thought to be a stream of particles. Later, it was reimagined as a wave. Newton and Huygens argued endlessly, each partly right. In the 20th century, quantum mechanics revealed the answer. Light behaves as both. Photons can travel like waves, interfering and bending, yet strike like particles in discrete packets of energy. This duality is not a flaw, but a feature of reality. Light is the bridge between matter and energy, between what is seen and what makes seeing possible. It carries information across the universe, from distant galaxies to your eyes in the space of an instant. To understand light is to glimpse the fundamental language of existence, an endless oscillation that illuminates not only the world around us, but the nature of knowledge itself. No one knew why the sky glows after sunset. When the sun dips below the horizon, the air still shines with soft golds and pinks. For ages, it was thought the sun's rays lingered magically. The explanation lies in scattering. Even after the sun sets, its light continues to pass through the upper atmosphere, where molecules and particles scatter the shorter blue wavelengths and let longer reds and oranges dominate. This effect, called twilight scattering, gradually fades as Earth's shadow climbs higher. Dust, pollution, or volcanic ash can intensify the glow, painting the sky in vivid streaks. The light we see is sunlight's echo, photons taking long, refracted paths through layers of air. Twilight is not an ending, but a transition. The sun's farewell filtered through the delicate chemistry of atmosphere and distance. For centuries, the nature of time itself has been one of science's deepest riddles. To most of history, time was a river that flowed evenly forward, carrying everything with it. Then Einstein showed that time is not universal. It bends and stretches with motion and gravity. A clock moving fast or deep in a gravitational field runs slower than one at rest. Time is woven with space into a single fabric, space-time. What we feel as seconds ticking is really the unfolding of relationships between events. Quantum physics complicates it further, suggesting time might not be fundamental at all, but an emergent property of change. The ticking of a clock, the beating of a heart, the orbit of planets, all are measurements of transformation. The mystery of time isn't just about flow, but about perspective, why it seems to move in one direction and why, even knowing its nature, we can never step outside it. The reason moving clocks run slow was once unimaginable. In everyday life, time feels absolute. A second here must match a second anywhere. But Einstein's theory of relativity overturned that certainty. When an object moves close to the speed of light, time for it actually slows compared to an observer at rest. This isn't illusion, it's measurable. Muons created by cosmic rays live longer when moving fast, and atomic clocks flown around the world return slightly out of sync with those left behind. The faster you travel, the more time stretches, until at light speed, it halts entirely. Gravity creates a similar effect, slowing time near massive bodies. To experience the cosmos fully, we had to abandon the notion of universal time. Each observer carries their own rhythm of existence, and the flow of seconds is no longer fixed but relative, a cosmic reminder that even time is flexible. For ages, the pull of gravity was known, but not understood. Everyone felt it, the tug that kept feet on the ground and made apples fall. Yet its nature remained mysterious. Newton described gravity as a universal attraction between masses, strong enough to bind planets to the sun, but he couldn't explain how it acted across empty space. Centuries later, Einstein solved the puzzle. Mass, he said, curves the fabric of space-time, and objects move along those curves. Planets orbit not because they're pulled, but because they're following straight paths in a warped geometry. This new vision predicted black holes, gravitational waves, and the bending of light, all later observed. Gravity isn't a tether, but the shape of reality itself, invisible yet absolute. Every step you take is a small interaction with the curvature of space, a quiet conversation with the very structure of the universe. The secret of how airplanes stay aloft took centuries to uncover. For most of history, flight was a dream reserved for birds and myths. Leonardo da Vinci filled notebooks with designs that never flew. People believed wings alone were enough, never understanding that air itself could bear weight. The secret lay hidden in physics. Lift arises from movement and pressure. As a wing slices forward, air travels faster over its curved upper surface and slower beneath. the pressure difference pushes upward. The Wright brothers proved it through persistence and measurement, learning to balance lift, drag, and thrust until their craft held steady in the wind. Bernoulli's principle and Newton's laws together explained what instinct could not. Flight isn't magic, it's a dialogue with the air, a partnership between shape and motion. Every aircraft today, from gliders to jets, repeats that simple lesson discovered in Wind and Patience, that even the sky obeys the quiet logic of pressure and flow. For a long time, no one knew what powered Earth's weather. Ancient peoples saw thunder as divine anger, wind as spirit, and rain as blessing. The idea that sunlight, gentle, silent sunlight, drives all storms was beyond imagining. Yet that's exactly what happens. The sun heats Earth unevenly, warming the equator more than the poles. Warm air rises, cool air sinks, and the planet's rotation bends those flows into trade winds and jet streams. Water vapor absorbs that energy, carrying it upward until it condenses into clouds, releasing heat that fuels storms. Each cloud, each gust, is a response to imbalance, the atmosphere seeking equilibrium. The weather is not random, but a living physics experiment repeating every day. From calm dawns to hurricanes, it's sunlight rearranging itself into movement, showing that power doesn't always come from force, but from the endless, patient working of warmth across air and sea. The reason hurricanes spin in opposite directions on different hemispheres baffled early scientists. For centuries, sailors noticed storms twist one way north of the equator and the opposite way south of it. The reason wasn't found in wind or ocean, but in Earth's own spin. As the planet rotates, moving air is deflected by the Coriolis effect, to the right in the northern hemisphere, to the left in the southern. When warm air rises from tropical seas, it creates low pressure, drawing more air inward. That inward flow begins to rotate, sculpted by the planet's motion into a spiral of astonishing order. The eye of the hurricane forms as air sinks and clears. From above, a storm looks alive, a vast whirl of vapor and gravity, symmetry born from chaos. The same rotation that brings us sunrise also shapes the fiercest winds on Earth, proof that even fury can be born from mathematics. For centuries, sailors wondered what made the ocean's surface glow at night. They called it sea fire, a ghostly shimmer that followed their ships through darkness. The light was alive, though no one knew how. It comes from bioluminescent plankton, microscopic organisms that emit light through chemical reactions of luciferin and luciferase. When disturbed by waves, they flash bright blue-green, painting the sea with living sparks. In tropical bays, entire coastlines can gleam like liquid starlight. This light produces no heat, just perfect efficiency. Energy transformed into visibility. For the plankton, it's survival, a flash that startles predators or signals others of their kind. For humans, it's wonder. What once seemed supernatural is life's own artistry, chemistry practiced by creatures too small to see. The ocean writes poetry in photons, and each wave is a line glowing softly before fading back into the dark. No one knew why some lakes turn pink. To early explorers, the sight of a rose-colored lake felt impossible. Surely some trick of reflection or minerals in the water. But the truth lay in life, not stone. Certain halophilic algae and bacteria thrive in extreme salinity, producing pigments like beta-carotene to shield themselves from sunlight. In heat and evaporation, their concentration grows, tinting the water deep pink. Flamingos feeding there absorb the same pigments, turning their feathers rosy too. These lakes, from Australia's Lake Hillier to Senegal's Lake Retba, are ecosystems balanced on a knife edge, beautiful because they're inhospitable. The color shifts with season and rainfall, breathing in rhythm with the world's salt and light. What seems alien is simply biology at its most determined. Organisms painting their own habitat to survive where almost nothing else can. For ages, the patterns of migrating animals were a great mystery. Each year, creatures vanished and returned as if following invisible roads through sky and sea. Ancient peoples guessed at instinct or divine guidance. Modern science uncovered tools of navigation woven into biology itself. Birds read magnetic fields through molecules in their eyes. Whales and turtles follow faint gradients of chemistry in the ocean. Monarch butterflies complete a 4-generation migration across a continent, guided by the sun's angle and internal clocks. Even tiny insects can orient using starlight. Migration isn't aimless travel, it's life's choreography, synchronizing survival with seasons. The Earth itself seems encoded into their senses. When the air cools or days shorten, that memory awakens. Move now, go home. What looked like mystery is inherited mapwork, proof that every species carries a fragment of the planet's geography inside its flesh. No one understood how the brain could store memories. For centuries, people imagined memory lived in the heart or soul. Only with the microscope did we begin to see the brain's secret. Networks of neurons forming, breaking, and reforming connections. Each thought leaves a physical trace, a strengthened pathway between cells, a pattern of chemical and electrical pulses. This process, called long-term potentiation, allows the brain to encode experience in structure itself. Remembering reawakens that network, replaying the pattern like music recalled by touch. Memory is not a static record, but a living reconstruction, altered each time it's summoned. When we remember, we also rewrite. The past is dynamic, carried in tissue that never stops changing. What seemed intangible is now understood as electricity made personal, the brain folding time into itself, shaping identity from the dance of charged particles. For centuries, the origin of language was an unsolved puzzle. How did sound become meaning? Early theories invoked gods, animals, or accident. The truth is quieter. Language evolved alongside cooperation. Early humans likely began with gestures, then shaped breath and voice into symbols for shared experience, danger, food, affection. Over time, syntax emerged, turning scattered sounds into structure. Our throats and tongues adapted for subtle articulation, and our brains grew regions dedicated to grammar and comprehension. Every language today carries echoes of those first utterances, the merging of thought with air. Linguistics traces patterns linking families of speech across continents, showing that language, like life, evolves. What began as necessity became identity. Words are fossils of emotion and logic combined, proof that the human need to connect is as ancient as hunger and as enduring as breath. No one knew how the mind could create consciousness. For millennia, thinkers separated matter and mind, assuming awareness belonged to spirit alone. But inside the brain, consciousness emerges from physical process, billions of neurons firing in rhythmic synchrony. No single cell knows who you are, yet together they generate self-awareness, memory, and perception. Information flows through loops linking the senses, the cortex, and the thalamus, creating an integrated picture we call reality. Science can describe the patterns, but the experience, the feeling of being, remains partly mysterious. Some theories see consciousness as the brain modeling itself, others as information becoming aware of its own flow. Whatever its root, awareness turns atoms into thought. The universe, through us, has learned to notice itself. That realization blurs the boundary between observer and observed, a quiet wonder that even thinking about consciousness is an act of it. For ages, the cause of mental illness was hidden in fear and superstition. Those who struggled were once seen as cursed, possessed, or weak. They were shunned or punished rather than understood. Only with modern medicine did the truth begin to surface. The mind is part of the body, and its suffering has physical roots. Imbalances in neurotransmitters, structural differences, and trauma can all distort thought and feeling. Psychiatry emerged to study these patterns scientifically, shifting blame to biology and environment. Today, brain imaging reveals how depression, anxiety, and psychosis alter neural circuits, not character flaws, but chemistry under duress. Therapy and medication can restore that balance, allowing people to rebuild lives once lost to stigma. The mystery of madness became the science of mind, and compassion replaced fear. Understanding mental illness turned superstition into empathy, proof that knowledge can heal both brain and heart. The way bees communicate their discoveries remained a mystery until the modern era. For centuries, people simply watched bees return from the fields, and suddenly the whole hive would rise into the air, heading in the same direction. It looked like telepathy. In the 20th century, Austrian zoologist Carl von Frisch decoded their secret, the waggle dance. Inside the dark hive, a returning forager performs a figure-8 pattern, waggling her body while moving forward. The angle of the waggle marks the direction of the flowers in relation to the sun, and the length of the dance tells the distance. Other bees follow, memorizing the instructions with their antennae. They then fly out and find the nectar, often miles away. This language works even as the sun moves, because bees adjust for its motion through time. The discovery revealed that insects can share abstract information. Every hum of the hive is a form of mathematics in motion, geometry translated into rhythm and flight. For centuries, people could not explain how seeds know when to sprout. To early farmers, a seed's awakening seemed an act of magic, dry husks turning to green life after rain. Inside each seed, though, a tiny embryo lies dormant, wrapped in protective layers and surrounded by food reserves. It waits for signals, the right mix of warmth, moisture, oxygen, and sometimes even light. When those cues arrive, hormones like gibberellin surge, enzymes activate, and the shell softens. Starches become sugars, the embryo swells, breaks its coat, and sends a root downward and a shoot toward the light. Some seeds need extremes, fire, freezing, or the stomach of an animal to trigger life. Germination is an ancient contract between organism and environment, timed perfectly to season and chance. What once seemed divine intention is nature's patient calculus, a chemical memory that whispers, "Not yet now." The mechanism that makes muscles move was once a complete enigma. Anatomists could see muscle fibers shorten, but no one understood the force behind it. Under microscopes, scientists later found billions of interlocking threads, actin and myosin, sliding past one another. A nerve impulse releases calcium inside the cell, letting myosin heads grip actin filaments and pull. Adenosine triphosphate, ATP, powers each microscopic stroke. Billions of these tiny interactions create every motion, from a heartbeat to a smile. The process converts chemical energy directly into mechanical work with extraordinary efficiency. Muscles aren't simple ropes tightening. They're living engines of coordinated molecules, rebuilding themselves even as they labor. Every blink, every breath, every step is a symphony of chemistry guided by electricity. What was once mystery is now understood as motion born from molecules, proof that power can come from perfect cooperation at a microscopic scale. No one knew how nerves carried signals through the body. Before electricity was understood, nerves were thought to be hollow tubes moving mysterious fluids. The breakthrough came when researchers discovered that nerves create and transmit electrical impulses. Each neuron holds a charge across its membrane. When stimulated, ion channels open and charged particles rush through, generating a rapid wave called an action potential. This pulse travels along the axon, leaping between insulating gaps to speed its journey. When it reaches the synapse, it releases neurotransmitters that bridge to the next cell. Millions fire together, forming the language of the nervous system. Thought, motion, and emotion are patterns of voltage repeated endlessly, so small yet so vital that a single misfire can alter who we are. The body is wired with lightless lightning, electricity translated into life's conversation, one spark at a time. For ages, it was unclear how we sense balance and motion. Long before science named the inner ear, sailors spoke of sea legs and dizziness as curses of the wind. Deep inside the skull lie 3 semicircular canals filled with fluid and lined with sensory hairs. When the head turns, the fluid lags behind, bending the hairs and sending signals to the brain about direction and acceleration. 2 nearby organs, the utricle and sacculae, contain crystals that shift with gravity, telling the brain which way is down. The information merges with vision and muscle feedback to maintain balance. When those systems disagree, we feel vertigo. This mechanism evolved long before humans. Fish rely on nearly identical sensors. Balance is not simply standing upright. It's constant conversation between motion and stillness, a physics experiment running inside us every moment we move. The way our eyes detect color was once completely misunderstood. To early thinkers, colors were inherent qualities, tiny bits of pigment carried by light. In the 19th century, Thomas Young and Hermann von Helmholtz proposed a radical idea. The eye has only 3 types of cones, sensitive to red, green, and blue. All other hues are mixtures of those signals. Later, microscopes confirmed it. Each cone cell contains a pigment tuned to a narrow range of wavelengths. Together, they allow the brain to calculate color from ratios of stimulation. The world's richness of shades exists only inside the mind. Color blindness arises when one receptor type is missing, reducing the palette. Light itself is just energy. The eye turns it into art. Every sunset, every painting, every memory of blue sky is perception painted by neurons interpreting waves, a reminder that beauty is a creation of sight itself. No one knew what made cats purr. For centuries, the steady vibration of a cat's purr was considered a mystery, perhaps a second heart, perhaps magic. Scientists later discovered that cats produce it by contracting muscles around the larynx in rapid rhythm, 20 to 30 times per second, during both inhalation and exhalation. Neural oscillators in the brain keep the pattern steady. The frequency is low, between 20 and 30 Hz, and those vibrations promote healing by stimulating tissue regeneration and bone density. Cats purr not only when content, but also when frightened or injured, as if to soothe themselves. To humans, the sound feels peaceful. To cats, it may be therapy. The purr is the biology of comfort turned audible, an ancient mechanism that turns breath into vibration and vibration into calm, binding 2 species through shared quiet. For ages, the glow of the deep ocean was a baffling secret. Early sailors spoke of ghostly lights far beneath their ships. The truth came with deep-sea exploration, bioluminescence. In the lightless abyss, countless organisms, from jellyfish to squid, create light through reactions between luciferin and oxygen. Some lure prey with dangling lamps, others flash to startle predators or attract mates. Many shine blue, the color that travels farthest underwater. Even bacteria glow, turning colonies into drifting constellations. Light in the deep sea is communication, camouflage, and survival all at once. Each flicker is energy made visible in darkness, as though the ocean itself refuses to be unseen. The abyss isn't empty. It's alive with silent fireworks, a slow, eternal aurora born not of sunlight, but of life, insisting on being noticed in the dark. The reason penguins never freeze was a mystery for generations. In temperatures that can drop below -60, penguins waddle calmly across ice and dive into near-frozen seas. Their secret lies in insulation and circulation. A thick layer of feathers traps air close to the skin, sealed by oil for waterproofing. Beneath that, a layer of fat stores energy and warmth. Blood vessels in their legs exchange heat efficiently. Warm blood moving outward transfers warmth to the colder blood returning from their feet, minimizing loss. When storms rage, they huddle by the thousands, rotating positions so every bird shares time in the warm center. Their feathers overlap like scales, shedding snow and water alike. Penguins are living furnaces designed by evolution to conquer cold, proof that survival can be engineered feather by feather until endurance itself becomes grace. For centuries, people wondered how birds could sleep while flying. Migrating birds can travel for weeks without landing, crossing oceans and continents. How could they survive without rest? Studies with tiny brain monitors revealed that some species, like frigate birds, let one half of their brain sleep while the other stays awake, a state called unihemispheric slow-wave sleep. They glide on updrafts, wings locked, switching hemispheres every few minutes. Others take hundreds of micronaps, seconds long, adding up to hours each day. Their brains are wired for vigilance, even in dreams. Sleep, once thought to require stillness, finds a way in motion. The sky itself becomes their bed, the wind their cradle. These travelers show that rest is not the absence of movement, but the mind's quiet rhythm, keeping life aloft even when the world beneath is endless sea. The creation of lightning inside volcanoes was once beyond explanation. When volcanoes erupted, ancient witnesses saw the sky itself ignite. Forks of white light leapt through pillars of smoke as if the gods were striking the mountain. For centuries, no one understood the cause. Only with cameras fast enough to freeze the chaos did scientists uncover the secret. Inside the ash plume, billions of tiny particles collide, breaking apart and stealing electrons from one another. Each impact charges the next, building an enormous electrical imbalance. When the difference becomes too great, the air discharges in violent bolts that illuminate the eruption. It is thunderstorm physics on a monumental scale, powered by ash instead of raindrops. Volcanic lightning is both fire and storm, matter grinding itself into electricity. What once looked like anger from the heavens is the mountain balancing its own energy, transforming friction, dust, and chaos into light. No one knew how long it took for light to reach us from the sun. The sun seemed immediate, its warmth on the skin, its glare on water, its rise and fall defining the rhythm of life. For centuries, people assumed that light must move instantaneously. Galileo tried to measure it by flashing lanterns from distant hillsides, but the delay was too small for the human eye to register. The truth appeared in the 17th century, when Ole Rømer watched Jupiter's moons vanish into eclipse at slightly different times depending on Earth's position in orbit. The pattern revealed that light travels at a finite but staggering speed, 300,000 kilometers each second. and that sunlight takes about 8 minutes to reach Earth. Every dawn we witness is already 8 minutes old. The light that opens a flower or warms your hand began its journey when you were still a breath away from waking. Even brilliance needs time to travel. The source of radio waves was a mystery when they were first detected. In the late 1800s, small sparks began leaping between metal spheres in physics laboratories. Sensitive instruments across the room trembled in response, even with no wires connecting them. Heinrich Hertz realized he had produced an invisible kind of wave, an electromagnetic vibration predicted decades earlier by James Clerk Maxwell. These waves were longer than visible light and could slip effortlessly through air and walls. A few years later, Guglielmo Marconi found that they could carry coded signals across miles of sea. The discovery rewrote communication. Sound, speech, and music could move without a medium. What began as laboratory static became the foundation for radio, radar, and Wi-Fi. Every broadcast, every whisper from a distant probe on Mars is the descendant of those first invisible pulses. The air around us is never silent. It hums continuously with the quiet voice of discovery. For ages, people wondered if sound could exist in space. Stories once imagined roaring comets and exploding stars echoing through the void. Yet when astronauts left Earth, they found only silence. Sound requires matter, molecules that can collide and transmit vibration. Space is almost empty. Its vast distances hold too few particles to carry any audible wave. But the universe does vibrate. Within nebulae, dense clouds of gas ripple with low-frequency pressure waves. Entire galaxies hum in radio frequencies, and black holes send tremors through space-time itself, gravitational waves that stretch and squeeze reality. Astronomers translate those signals into audible tones, so we can hear what physics alone perceives. The cosmos is not truly quiet. It sings in dimensions we cannot sense. Between those unheard notes lies the stillness that makes the stars seem eternal, a silence large enough to hold every sound that ever was. The strange shapes of clouds once inspired myths before meteorology explained them. Long before weather charts, people read the sky like scripture. Towers of white became castles of spirits. Streaks of cirrus were the breath of dragons. In the early 19th century, an amateur scientist named Luke Howard gave those shapes their modern names, cumulus, stratus, cirrus, and showed that clouds obey physics, not prophecy. They form when rising air cools and water vapor condenses into droplets or ice crystals. The shape tells the story of motion. Gentle layers mean stability. Vertical columns reveal turmoil. Cumulonimbus towers announce thunder long before it sounds. Watching them, we glimpse the invisible machinery of the atmosphere, turning heat into form. What looked like divine art is really air sculpting water, a reminder that beauty and explanation often coexist perfectly in the same sky. No one knew why rain smells so earthy and sweet. The fragrance that rises when the first drops hit dry ground is older than humanity. Farmers called it the smell of dust awakened, but only in the 20th century did scientists isolate its cause. During dry spells, plants release oils that seep into soil and stone. When rain arrives, falling drops trap tiny bubbles of air that burst on impact, spraying microscopic particles upward. Among them is geosmin, a compound made by soil bacteria, detectable by the human nose at mere trillionths of a gram. Together with plant oils, it becomes petrichor, the perfume of returning water. That scent links weather, soil, and life in one moment of renewal. Every shower is a chemical reunion between sky and earth, the planet exhaling after thirst, reminding us that even smell can be a language of survival. For centuries, people wondered how crystals grow deep underground. Caverns lined with quartz seemed impossibly deliberate, as if carved by invisible hands. In truth, crystals are order emerging from chaos. When molten rock cools slowly or mineral-rich water evaporates, atoms arrange themselves into repeating lattices, mathematics made solid. Each change in temperature or pressure alters the rhythm of growth, shaping facets and color. A flawless gem records thousands of tiny environmental shifts like pages in stone. Amethyst, diamond, salt, all follow the same geometry written in their atoms. Crystallization is patience measured in time rather than thought, the universe seeking balance through symmetry. What miners once called magic is simply matter choosing the most beautiful way to rest. The reason desert sand can sing was once unknown. Travelers crossing certain dunes heard the ground drone like a low cello, a sound rolling for miles through empty valleys. For centuries, explanations ranged from spirits to hidden storms. The secret lies in physics. When dry grains of nearly identical size cascade down a steep slope, they rub and vibrate together in synchrony, compressing air and releasing a steady, resonant tone. Each dune has its own note, shaped by grain diameter, moisture, and heat. Some roar, others hum softly. The sound can last for minutes, deep and haunting. Singing sand is friction turned into harmony, proof that even silence can be coaxed into music when nature finds perfect rhythm. The desert may appear lifeless, yet under the right conditions, it literally sings the memory of the wind. No one understood how geckos could walk up walls. To early naturalists, the little lizard's abilities seemed supernatural. No claws, no suction cups, yet it scurried across ceilings with effortless grace. Under microscopes, scientists discovered millions of microscopic hairs, CT, on each toe, branching into hundreds of even finer tips. These interact with surfaces through van der Waals forces, the faint electrical attraction between molecules. Each contact is weak, but together they produce enormous grip, enough for a gecko to hang by a single toe. By changing the angle of its foot, it releases instantly without sticking. Engineers now imitate this design to create adhesives that climb glass without glue. The gecko's trick is not magic, but subtle physics. Strength born from gentleness, adhesion through invisible connection. For ages, the slow drift of the magnetic poles was a hidden story inside the Earth. Compass needles were once thought infallible, yet early explorers noticed their direction slowly shifting. Beneath Earth's crust, molten iron moves in swirling convection currents around a solid inner core. Those flows generate electric fields that combine into a vast magnetic field. As the currents change, the poles wander across the planet, sometimes reversing entirely, north becoming south. Rocks preserve these flips in their magnetic alignment, revealing a restless geodynamo that has operated for billions of years. The field shields life from solar radiation and guides migratory animals through instincts older than maps. Its movement is a reminder that the planet's heart is liquid, dynamic, alive, beneath a thin, fragile crust. The ground feels steady, but even direction itself is slowly shifting under our feet. The mystery of how Saturn's rings stay in place is now beautifully solved. When Galileo first looked through his telescope, he thought Saturn wore ears. A century later, Huygens realized they were rings. But how could something so thin and delicate survive? The answer is gravity's subtle choreography. Each fragment of ice and dust orbits Saturn at its own perfect speed. Moons called shepherds travel alongside, their gravity tugging and sculpting the ring edges into razor-sharp boundaries. Collisions between particles flatten the disk, damping chaos into order. What looks static is constant motion, a trillion collisions a second creating equilibrium. Over time, sunlight and micrometeorites slowly erode the rings, but new material also drifts in from moons. They are transient and eternal at once. Frozen rivers orbiting a world of storms, balanced by mathematics so precise that chaos itself keeps them whole. For centuries, the reason tides are higher during a full moon was unclear. Long before astronomy, coastal people learned to read the pull of the sea. They knew that the highest tides came when the moon was full or new, yet the connection seemed mystical. Only later did science reveal the truth. Tides are the ocean's slow response to gravity. The moon's pull lifts water on the side facing it, while inertia creates a second bulge on the far side. The sun's gravity joins the dance, aligning during full and new moons to make spring tides, and pulling sideways at quarter phases to make neap tides. The whole planet flexes slightly as water follows these cycles. Every wave that curls against the shore echoes that cosmic rhythm, a physical link between the turning Earth, its companion moon, and the great star that lights them both. No one knew how the ozone layer formed high in the atmosphere. Invisible, odorless, yet vital, the ozone layer shields Earth from ultraviolet radiation. For centuries, no one knew it existed. Ozone is a form of oxygen with 3 atoms instead of 2, created when intense sunlight splits O2 molecules. Free atoms recombine into ozone, which in turn absorbs more ultraviolet light, breaking apart again. This delicate cycle sustains itself high above the clouds. When human chemicals like chlorofluorocarbons began destroying ozone, holes opened over the poles, threatening life below. The discovery led to one of humanity's greatest environmental success stories, the Montreal Protocol, through which nations acted to phase out those compounds. Today, the ozone layer heals slowly under the same sunlight that once formed it. A fragile veil, constantly renewed, reminding us that protection can emerge from destruction itself. The way birds see ultraviolet light was once unimaginable. To us, a robin's red breast or a peacock's feathers already dazzle. But birds see even more. Their eyes have 4 types of comb cells, one sensitive to ultraviolet light, invisible to humans. Under that hidden glow, flowers, fruits, and even feathers reveal patterns of contrast and symmetry. Birds use these cues to find ripe berries, spot prey, and choose mates by markings we cannot perceive. Some species navigate using ultraviolet reflections from the sky's polarization. What looks plain to us might blaze with hidden color to them. Their vision reminds us that reality depends on perception. The world is always brighter, deeper, and stranger than we can see. It's our senses that narrow the view, not nature that lacks beauty. For ages, the patterns of brainwaves during sleep were a complete unknown. Before machines could read the brain, sleep seemed like silence, a nightly blackout. Then, electrodes revealed rhythm when none was expected. During deep sleep, slow delta waves roll through the brain, repairing and restoring. Lighter stages show faster oscillations as memories replay and stabilize. In REM sleep, activity bursts in patterns nearly identical to waking thought. Each night, consciousness dissolves into this electrical sea, organizing itself anew by morning. Dreams weave emotion and memory together, giving meaning to experience. Sleep isn't rest so much as internal maintenance, a nightly reset of mind and body. What once looked like unconsciousness is now seen as one of life's most active, essential states, proof that even stillness can be a form of creation. The origin of electricity was once a mystery tied to amber and silk. Ancient Greeks noticed that rubbing amber with fur made it attract bits of straw. They called the phenomenon electron. For 2,000 years, it remained a curiosity until scientists like William Gilbert and Benjamin Franklin discovered its nature, charged particles moving through matter. Alessandro Volta built the first battery. Michael Faraday found that changing magnetic fields produced currents, and James Clerk Maxwell united electricity and magnetism into a single force. Electricity was no longer magic, it was motion itself, the hidden energy of electrons in every atom. Today, it powers everything from neurons to cities, but its essence is the same spark once drawn from amber. The modern world was built on a single ancient observation that even in stillness, matter holds energy waiting to flow. No one knew why sound travels faster in water than in air. For centuries, sailors noticed that oars struck water before the echo of their splash reached the ear. Sound, it turns out, moves by vibration, molecules knocking into one another. In air, those molecules are far apart. In water, they are tightly packed, passing vibration more efficiently. Sound in water travels about 4 times faster than in air. Marine animals have evolved to use this. Whales communicate across entire oceans, dolphins navigate with sonar clicks, and submarines map the sea floor with echoing pulses. Water thickens and amplifies sound, transforming vibration into reach. The next time you submerge your head beneath the surface and hear the muffled world, you're listening through a medium built for sound, a reminder that silence is only relative. For centuries, scientists struggled to understand why magnets have 2 poles. Magnets are inseparable pairs, north and south bound together by invisible force. Cut one in half, and each half forms its own poles anew. For a long time, no one knew why. The answer lies in the electrons inside. Each spinning electron is a tiny magnet in magnetic materials. Billions of them align in the same direction, creating a unified field with opposite ends. Their symmetry cannot be broken by slicing the object. It simply reforms. Physicists still search for the elusive magnetic monopole, a particle with only one pole, but none has yet appeared. Magnetism seems to insist on duality, its strength born from balance. Attraction and opposition are not enemies. They are the same phenomenon seen from opposite sides of the same field. The strange expansion of the universe once defied every expectation. When Edwin Hubble measured galaxies in the 1920s, he found they were all retreating, the universe expanding in every direction. Astronomers assumed that gravity would gradually slow the motion. Instead, later observations revealed acceleration. Some unknown energy, now called dark energy, is pushing space itself apart. Galaxies drift farther away each second, the fabric of space-time stretching faster as it grows. We still don't know what dark energy is. It may be a property of space or something entirely new. But we do know what it means. One day, the light from distant galaxies will fade beyond view, leaving only the faint glow of our own. The expansion of the universe isn't a bang. It's a continuous unfolding, an invisible wind carrying everything toward infinity. No one knew why time moves differently near massive objects. For Newton, time was constant, flowing the same for everyone. Einstein changed that forever. His general theory of relativity showed that gravity is not a force, but the warping of space-time by mass and energy. Near a massive object, space curves and time slows. Clocks tick imperceptibly slower on the ground than atop a mountain, and satellites must correct for this effect to navigate accurately. In the presence of a black hole, time nearly stops at the edge. The closer you fall, the slower the seconds pass, until, from outside, you seem frozen forever. This is not illusion, but geometry itself. Time stretched by the shape of reality. What feels like uniform flow is actually flexible, personal, and alive, bent by every planet, star, and breath in the cosmos. The world is quieter now. The questions that once burned bright have softened to embers, glowing quietly in the dark. We've walked together through centuries of wonder, mysteries that once baffled the greatest minds, now woven into the rhythm of understanding. And yet, the feeling that first drew us to those mysteries still remains. That small spark of curiosity, the same one that made a child look up at the stars, or an explorer listen to the sea, it's still there, gently alive inside you. Science has given those wonders names and reasons, but never taken away their magic. Every solved mystery leaves behind a trace of awe. The sun still rises like a question answered again and again. Lightning still dances across the sky as if it remembers being misunderstood. The quiet between waves, the echo of the moon's pull, the shimmer of dust under sunlight, all remind us that truth and beauty are never far apart. So as you rest, let your mind drift among the things we now understand, not as facts, but as lullabies of the world. The stars are burning, the oceans breathing, the earth turning slowly beneath you. You don't need to think or know or search anymore. The universe is still awake, and that is enough. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. For now, just breathe. Let your thoughts fade like waves on the shore. Let the warmth of the world cradle you in its quiet rhythm. The mysteries have all been kind tonight. They've shared their stories, and now they rest with you. Good night.